Okay, so this is an exam review for the first exam in GIS 101. Some of the things that you need to remember are the definition of things like geospatial technology. I might ask you, what is geospatial technology? And you would tell me things that use several techniques to analyze, acquire, manage, and store and visualize data that comes from GIS, GPS, remote sensing, various apps, and the internet. Who uses it? All these different kind of agencies. A likely question would be to name 3 or 4 agencies that use geospatial technology, and then how. And so you could tell me, the government might use it for the military for navigation, forestry might use it to inventory um, timber stands, public health could use it to track disease outbreaks, biologists to identify and delineate wetlands, humanities might use it to look at population dynamics and demographic related information, that kind of stuff. What is geospatial data? It's a good question. It's not just data and information, it's something that's understandable. It involves locations and attributes more often than not. It comes from lots of sources and lots of formats. Probably won't ask you anything about the geography side there. Geolocation, I will ask you about that. Techniques to determine where something is. The W3C geolocation API is just something that they talk about in the textbook a little bit. I'm not going to go into too much detail about that. Geotagging, which is when you embed location information with a photograph. That is something that you might want to also know. More questions on this exam will come from this next set of information. From the where in the geospatial world are you? You need to know what a datum is, a GCS. You need to understand the UTM and the state plane coordinate systems. So what is a datum? If I ask you what a datum is, you should tell me it is how we fit a specific ellipsoid to a geoid. If I ask you what a geoid is, you're going to tell me it is a gravity-based imperfect shape for the surface of the Earth. And if I ask you what are some common datums that we use, NAD27, NAD83, WGS84, that should come to mind. If I ask you what a transformation is, you should tell me that is what happens when we go from one datum to another. That is a transformation. When we go from one projection to another, that's simply called a projection. Might give you a picture, something like this, or something to that effect, and then ask you to identify these layers. Or I might ask you a simple question like, explain the difference between the Earth, the geoid, and the ellipsoid. And in a situation like that, you would say something like, the Earth is it's a rocky surface that goes above and below the sea level. The geoid is a surface that we define as sort of zero elevation, and it is based off of the gravitational pull of the Earth, and so it's a gravity defined area. It is oftentimes synonymous with mean sea level, but it is not the same thing. It is measured and calculated differently, but the closest thing that you can see to visualize it is sea level. And of course the ellipsoid is that perfect mathematical shape, defined major and minor axis, and we simply fit the ellipsoid to the geoid, and then we have a datum. If we talk about geographic coordinate systems are they're global systems that help you figure out where you are. They run in lines of latitude and longitude. Latitude run parallel to each other. Longitude run, not rune, pole to pole. They're closer at the poles and they're further still apart from each other at the equator. The equator is sort of that midpoint between the poles. The prime meridian is the longitudinal line from which we start measuring east and west. Degrees, minutes, and seconds. Decimal degrees are how we calculate these angular degrees in GCS. We can't visualize geographic coordinate systems. They create too much distortions. And they're for objects that are rounded, so you can't measure things like distances and areas very good. We use map projections. Map projections take these round objects that we're calculating these GCSs from and convert them into flat two-dimensional maps. We call those projected coordinate systems, or PCSs. One of the oldest ones we know about is the 1569. What was created in 1569 by Mercator. It was used for navigation. It dramatically distorts size. It is a cylindrical projection. There are other types of projections, azimuthal, which are flat planar projections, conic projections, cone-shaped. All these different things go together to tell us more about things like the universal transverse Mercator system or the state plane coordinate system. We're not going to really put any questions on the exam about the U.S. National Grid or the Military Grid reference system. So, cylindrical, conical, and azimuthal. These are the different types of basic underlying ways in which we would develop a projected coordinate system. This is a cylindrical projection, and cylindrical projections like this tend to distort size, and this is noticeable because Greenland is the size of Africa, but Greenland is only 1/17 the size of Africa. We use cylindrical projections a lot. This is the UTM system. And it is a transverse or a sideways cylinder that we spin around the Earth, creating 60 zones. Each zone is 6 degrees wide. That covers the entire 360 degrees around the planet. Anything within a zone is relatively accurate. As you move outside of a zone, that particular projection is no longer accurate. We talked very briefly about geocoding and how it works. But more specifically, when we're talking about not just so much the geocoding on street addresses, but literally the coordinate systems for things like the UTM system, you might have a zone like this one here in the picture, 13 north, and it falls between those certain lines, 108 degrees, 102 degrees. That difference being 6 degrees, which is the width of a zone. 13N would be exactly 3 degrees from either side. And then you would have the actual coordinates within that zone is the number of meters to the right and up. And that's all it is to calculate these locations. Right and up. Different states have different state plane zones. Lots of different ones, different kind of projections. Some are UTM, some are conic, some are, they could be just about anything, depending on where it's at. But the key thing to remember here is states decide how many zones they need, and from that you kind of get this general idea of the shapes of the states and where they would be projected good or not. For example, if you're looking at Kansas and I ask you in the state plane zone coordinate system, what is best for Kansas? If it's in the northern part of the state, it would be Kansas north. If it's in the southern part, it would be Kansas south. If we're looking at the entire state of Kansas, it may not be the state plane zone because Kansas has 2 state plane zones. We may have to look at something like a UTM zone or modify something. Nebraska, however, there's only one state plane zone, so we can assume that everywhere in Nebraska is fine. What happens when we have data from different projections? It makes the stuff look very, very differently. Here we have two maps of the same place, one in Mercator and one in Lambert Conformal Conic. And you can see that it is dramatically different. And so we have to, in order to fix this, change one to the other to match the other one. And that's something we call reprojecting. If you take data from one projection and change it to another, it's not really a big deal if they're in the same datum. It's a slightly bigger deal if they're in different datums. That requires an additional step called a transformation. That's when you shift from one data to another. A bigger problem is when you lack spatial reference information at all, in which case you then have to figure out what that is. One of the reasons that the data changing from one datum to another is more complicated is because, remember, datums are based off of a specific ellipsoid, and here we have a map of a couple of different ellipsoids in the geoid and how they line up. And you can see how you might take something like the Clark 1866 and shove it up against that geoid layer for a particular location in a local type projection, and it would be fine. It would be really, really off in a lot of other places. Whereas the GRS 80 and the WGS 84 ellipsoids are much, much closer to the geoid in general. And so they tend to, and they are designed for global projection systems. Once you identify all the locations, once you identify a location and like on a map, you want to look at that in 3D, and it's an old map, you can georeference it. Georeference it is nothing more complicated than identifying the coordinates of different things on that image so that it will display properly in a GIS. Identification of known locations on data with unknown spatial reference and corresponding same location on data with a known spatial reference. Think of it as aligning unreferenced data or map to a reference data layer or map. That is georeferencing. We do it by identifying control points. In this case, we're using two images. One is spatially referenced as one is not. We simply identify common locations from one place to the other, from one image to the other. And what this does is it allows us to generate these control points, these paired locations that we can then allow the software to use to fix these things. And so you identify a bunch of locations, and you can see how it shifted this picture around to sort of that configuration, and then it would line up with the image that you see on the right. When we do transformations like this, or when we do georeferencing like this, the way that it works is through a combination of techniques. The first one being rotation, which is simply where you just twist the image around. Skew is sort of when you grab the top and bottom and drag them in different directions. It sort of twists it a little bit that way. You can also do translation, where you just simply shift the entire image, and then scaling if you need to make something bigger or smaller. Ultimately, that's how you take a map like this and fit it over top of a map like the one behind it. And you can see from this how this has been twisted and shifted and went through some of those other processes. Watch these videos. It will be helpful to help you understand what we were talking about in class. I might even sneak in a bonus question or something. Never know. Or it could just be a trick to get you to watch the videos. I'll leave that up to you. Once you do georeferencing, it's not the end of the process. You have this idea of rectifying the image or updating the georeferencing. Updating georeferencing creates a file that goes along with the image that tells the GIS software how to display it. Rectifying it creates a brand new image that has already been bent and twisted, if you will, to fit the given projection that you want. And this new image is then populated with information from the old accordingly. And in order to do this to create this new image, You have to go through this process of resampling, which can cause some distortion, blurring, or smoothing of your data, but that is generally acceptable. Here is an image of a georeferenced map over an aerial photo of modern England. And this is a map around Exeter College, and this is a very old map, but once they identified locations that were common in both with the georeferencing process, the new digital image of the old map became spatially referenced, and it can now be displayed with the aerial photo. Also, there will be a vocabulary section on this exam. This section is part of that list we did from the very first test. It's terms 23 through 33, and here they are on the list. They're also on the vocabulary list I emailed everyone, so there's no lack of ability to get these, other than just need to study.